Ladies and gentlemen, we now proceed with the next keynote address, and it is my pleasure to introduce to you the next speaker, Gary Gack of Process Fusion Net USA. Gary has more than 40 years of diverse experience in the software and IT industry, including more than 20 years focus on process improvement. He is the author of numerous articles and a forthcoming book entitled Managing the Black Hole, The Executive's Guide to Software Project Risk. He holds an MBA from the Wharton School and is a Lean Six Sigma Black Belt. In addition, he is an ASQ Certified Software Quality Engineer and also Certified Scrum Master and a visiting scientist with the Software Engineering Institute, where he co-authored Measuring for Performance-Driven Improvement. Ladies and gentlemen, please welcome Gary Gack.
Hearing me out there all right? Okay, there, I'm back on. Okay, well, I'm very pleased to be here again this year, and special thanks to Mastura and all of her great team. They have done a wonderful job again this year. So with that, I will jump right into this. My agenda for today, I want to make a few remarks about some of the statistics that are available about our success rates and failure rates. Probably many of you know who've been involved in software for a while. It's quite a risky business. I want to cite a few statistics. And then I want to talk about a cost of quality model where we're going to discuss defect insertion and removal benchmarks. There's a lot of published information available. We're going to talk about some of that and talk about how we can use it in a very practical way. And then I'm going to talk about how we might begin to apply some of the ideas I'm going to talk about today. So some grim realities. This is some data from the Cutter Consortium, which is a consulting and statistics organization in the U.S. that does extensive surveys of software project results. Some recently published information, 62% of the projects they sampled exceeded the schedule by more than 50%. 64% were over budget by 50% or more. And 70% of those surveyed had serious quality defects. So I'm not sure so much about most of the statistics that are available come from the US and from Europe. There's a little less data here in Asia. I'm not sure that the results are very different from what I've been able to ascertain. These are pretty representative statistics for mostly larger software development projects. Certainly small projects, a few person months of web system development, the results are much better than this. But in the big efforts, where we're, say, maybe 10 person years of effort and above that, success has been at least elusive. We have not had great results in bigger efforts. So there's some key implications of this. If we want to improve outcomes, have better results in the future, one of the key things we need to do is manage commitments. So we need to start our projects in a way where the schedule we've committed to, the budget available, and the quality expectations are mutually consistent. And probably many of you have been in a situation where there's an expectation that you're going to deliver a system of a certain scope, and management has dictated that that's going to be done in some amount of time, 6 months, 12 months, whatever. And I know many of us have been through the situation where the schedule that's been laid down is entirely inconsistent with the scope of the project. So the major takeaway here is we cannot commit ourselves to run 3-minute miles. Some of you may be familiar with the world of track. When you run a mile, the world record is something like 3 minutes and 40 seconds. And yet I've seen many projects that had an initial schedule that was analogous to a 3-minute mile. In other words, if you looked at the historical data that exists in the industry, there are no examples where a project of a certain size has been done in the amount of time that's been allocated for it. This is very common. I've been involved in a couple of dozen turnaround situations where I was called in after a project had been running for a while, was already in a lot of trouble, late, over budget, various issues had arisen, asked to do an assessment, and I would say about 80% of the time, one of the key findings was that the original schedule was never realistic. There were no examples where any team had ever delivered a project of the scope in question in the time that had been allocated to it. And of course, when that situation prevails, when that's the situation you find yourself in, the inevitable result is that we start to de-scope. We start to cut off things that had been asked for. We'll say, well, we're not going to deliver this feature, we're not going to deliver that feature, but frequently we're well into a project, halfway, maybe even further, before reality becomes clear, before people accept the fact that they're seriously behind schedule and seriously over budget. And so at that time they've already made a lot of investment in finding requirements, perhaps doing design. So when we start to de-scope requirements, start to de-scope what we're going to deliver, that means we've got a lot of wasted effort we've put into designing components that will never be delivered, or at least won't be delivered in the initial delivery. So key implication of this is, you've probably heard the expression speed kills, referring mainly to driving. There's plenty of industry data that quantifies the impact of schedule pressure. So when we are required, or sometimes it's a self-inflicted wound, we're too optimistic, and we commit ourselves to deliver on a schedule that we're not going to be able to meet, we call that schedule pressure. Schedule pressure is often imposed by management, sometimes we impose it upon ourselves, but the impact of that kind of situation has been quantitatively modeled by a number of different folks. Capers-Jones recently developed something called Riskmaster that quantifies this. Previously, he developed Knowledge Plan with SPR. Gallerath has an estimating model. Larry Putnam has an estimating model. And all of these tell us the same thing. You can actually simulate the effect of various degrees of schedule compression. So you can let the model recommend to you what would be a realistic schedule, and then you can say, well, what will happen if I reduce that schedule? Or what will happen if I expand that schedule? Tools like these allow you to model that and do simulations and understand the realm of possibility, range of possibilities. And as schedule is compressed, what these models clearly tell us is two important things. One, risk goes up, and two, quality goes down. And those are not matters of speculation. These are as near to the laws of physics as we get in the world of software. So the impact of schedule pressure is especially dramatic as projects get bigger, and generally I'm talking about projects that are in the, say, 10-person years, 1,000 function points, and larger kinds of systems. When we compress the schedule unreasonably, costs will go up dramatically, sometimes as much as a factor of 2 or 3, and also the delivered quality is going to go way down. There may be 5 times as many defects delivered when we're operating under a very compressed schedule. And of course, the risk of outright failure goes up too. Much more likely that a highly compressed schedule project is going to end up being canceled. So again, this is not speculation. The data supporting these assertions is very extensive. Many tens of thousands of projects have been modeled by these several companies and a few others. And invariably, when we compress the schedule, the kinds of consequences I'm talking about always appear. So what's a key takeaway? Don't set a schedule you cannot meet. And I recognize that sometimes we inflict it on ourselves, but very frequently it's a management mandate. We're not really given a choice. We're told you will do this in a certain amount of time, and it's difficult to get management to listen. But I think it's one of our jobs. One of the speakers yesterday, I think, or maybe it was the day before, I've forgotten, spoke about the notion of being a test advocate. And I think one of the tasks of a test advocate, a very challenging, difficult task, is to try to educate the people who set the schedule, try to educate the top management, the people who set the budget, about what the consequences of their decisions are likely to be. And there's plenty of data around. You study up on this in my book, many others, books by Capers-Jones, by Larry Putnam, lots of others, have talked about this at length. So a second key implication of all this, if we want to get better results, is we really need to manage defects. And I would argue that the most important key metric associated with defects I refer to as total containment effectiveness, or TCE. And that's a real simple measure. That says count the number of defects you find before you release the product, divided by that number, plus the number of defects found after the product is released, over some agreed time period. Maybe it's 3 months, 6 months, 12 months, depends on the product. So by way of an example, very simple example, if we find 80 defects before we release the product and 20 more are found after the product is released, we have a containment rate of 80%. U.S. average right now is around 85%. Best-in-class companies are getting into the 99s. And we're going to talk about what the economic consequences are of those alternatives. Where you are in this total containment range has a profound influence on what your costs are going to be and how long it's going to take to get done, as well as, of course, the delivered quality. So, moving from 85%, again, that's about an U.S. average number, to 95% total containment effectiveness will reduce your cost 20 to 30% and your cycle time or elapsed time to do the project by 15 to 25%. Now, some of you might find that surprising. I know when I talk about these numbers to management audiences, I often get a lot of pushback, but the pushback is opinion-based, not based on data. These assertions are based on data. To quote Capers-Jones, defect removal efficiency, what I call defect removal effectiveness, he calls, and some others call defect removal efficiency. A little later on, I'll differentiate between effectiveness and efficiency. They're not really the same thing. But using his terminology, defect removal efficiency is among the easiest and most useful quality metrics, with less than 5% of the companies that he visits use it. And he regards that as professionally embarrassing to the industry. He calls that failure to use this malpractice. So in malpractice, at least in the United States, if you are a licensed engineer or a medical practitioner or a lawyer or certain other professional classifications, if you fail to use acknowledged best practices, that is malpractice, and you can be sued. I'm not sure how that works here, but I imagine a similar idea it probably prevails in most countries. So everyone in this room, everybody who's concerned with software development and software quality needs to understand TCE and use it. And there's a related thing that I call defect containment effectiveness, and that's a phased view. So across the project as a whole, we can measure total containment by saying how many defects did we find before we shipped, divided by that plus those found after shipment. But we can apply that same concept phase by phase, or iteration by iteration, if we're talking about an agile kind of a context. So another takeaway for this is, I think we sometimes have a little too much focus on process, and in no way do I want to say process is unimportant, but what's really important in the end is performance. Process is there only to ensure better performance. It has no merit in itself. So performance is about facts and data, a Six Sigma perspective on the view of the world. It's not so much about compliance like CMMI or TMMI. And I'm not dismissing the importance of those things either. It is important to have defined process. It is important to follow the process, but you can have a defined process for making concrete parachutes. But concrete parachutes really aren't very effective. They don't deliver the performance you want. They won't save your life. So it's important to focus on actual performance. Any process can produce good performance or poor performance, depending on how it's used. Another thing I want to say, which might be a little controversial for this audience, testing, as it's usually understood in the narrow sense, test software that's been built, is never going to be enough to get you into the 95 or higher total containment range. You will need to use other methods, additional methods, such as Fagan-style inspections, consistent with IEEE standard 1028. It is important that we test in the general broad sense of the word, not just the code that has been built, but long before that, we test the requirements, we test the design. And of course, we can't execute requirements and we can't execute design, so testing needs to be understood in a little bit of a different way. Sometimes we call those reviews, sometimes we call them formal peer review processes such as inspections. But anyway, failure to do that, again, I would regard as malpractice. It is essential that we focus on finding defects throughout the life cycle, throughout the process, as early as we can. So key takeaway from this, again, this will be controversial for a lot of people who've thought about how you manage software traditionally. You need to manage quality goals, not schedule. Now, I know that's controversial. Everybody's asking, where do we stand? Are we on schedule? And of course, schedule's important, but in the end, you're going to meet your schedule and meet your cost goals and reduce your risk and deliver a very good product if you focus primarily on quality. If that's your management focus, you're going to get much better results. Again, getting management to listen to this message is tough. It's a challenge. But the title of my talk is When Software Quality Goes Up, Cost and Schedule Go Down. So I'm going to try to demonstrate to you why that is the case with some numbers. I want to return to this idea about efficient versus effective. I think the distinction is an important one, and often these terms are kind of used a bit interchangeably as though they were the same thing. They really are not. We're effective if we do the right things, if the software we build is really valuable, it performs useful functions. It's not just a collection of features, not just a bunch of things that somebody wished they could have, but things that actually result in some kind of business value. And quality, at a minimum, meets expectations. Ideally, it exceeds expectations. On the other hand, we're efficient, and efficiency is what I'm going to focus on in the remainder of this talk. We're efficient if the value of what we produce, the output, is significantly exceeds the costs or values of the inputs, the labor we use, the resources we use, the time we use. So productivity measures efficiency. It does not measure effectiveness. So we could be very efficient but producing something that's useless. That is not effective, but it could still be efficient. You can be effective and inefficient. You can be inefficient and effective. Important to get clear the distinction between them. So oversimply stated, productivity is the ratio of output to input, but that's kind of a deep swamp because there are many things that influence that. It's much more complicated than that. We're not going to go into that today. So I want to talk a little bit about software cost of quality by way of getting to hopefully convincing you that when quality goes up, cost and schedule go down. We can think of software cost of quality, and there are other ways to look at this, but this is one, I think, useful way to look at it. The cost of producing, the costs associated with quality include costs associated with canceled projects. Now that's not frequently looked at, but I asked Capers to give me some data from his very extensive database on what the canceled project rates are for various application domains, and you see them listed here. And I use 20% because probably most of us, or a large percentage of us, tend to work more in business applications or management information systems, MIS. So I use that as kind of representative. And his data say that 20% of those projects are canceled outright. He's also got some data on how far along they are and how much money gets written off. So anyway, one element of cost of quality is effort we devote to projects that never deliver. And if you're in the field very long, you've probably experienced one of those at least, and maybe a few of those. They're not rare. So 20% are canceled, 80% are completed. So let's call that segment of our cost of quality A. And then in the completed portion, I've highlighted here, this is some data again from Capers that is activity-based costing data that he's been collecting for many years. He has this for tens of thousands of projects. One of the earlier speakers talked about activity-based costing. So here's a list of activities, the activity breakdown that Capers uses, requirements, prototyping, architecture, etc., etc. I've highlighted in yellow here those that are associated with the cost of quality. In other words, they are activities that are principally concerned with finding and removing defects. When I'm using the term defect, I'm using that in the broadest sense of the term. A missing requirement is a defect. A unnecessary requirement is a defect. So thinking about, in the broadest sense, Professor Azuma talked about some fine distinctions of what we mean by quality. When I speak of defects, I'm talking about all of those things. I'm not trying to get more narrow than that. If the customer believes it's wrong or it's incomplete or it's incorrect, it's a defect. And it is. I don't want to get into the fine distinction of did we meet the spec. If the spec was wrong, that's a defect. So I'm thinking about defects broadly. These highlighted activities are things that have to do with finding and removing defects. So they're cost of quality elements. And Capers has quantified in terms of hours per function point the effort that is devoted in projects to these kinds of activities. And they total up 42% of total effort, according to his data, is devoted to finding and fixing defects within a project budget. So let's call that B. Then there's a third thing, C, and that is a consequence mainly of the issue I discussed earlier. When we have excessive schedule pressure, we get partway into the project and we start dropping stuff. So that's de-scoped features. And whatever effort we devoted to defining the requirements, doing the design, whatever other work we did, sometimes some of the coding, we're going to throw that away. So that's another cost of quality. It's not value-added delivered. Hard to say what that number is. I've not been able to find any real good data on this. In conversations with Capers, we kind of came to the conclusion that 10% seems like a reasonable number. we don't have hard data to support that. So when you take all this stuff together, what you end up with is a total non-value added value of 60% of software resource. Now, most people find this staggering and they say, oh no, this can't be true. That's not the way it is where we are. No way. Well, I've heard that story many times, and I've had the opportunity dozens of times to go in and help organizations actually measure that. Very rarely is it less than 40%, and most of the time it's much closer to 60 than 40. So there's an awful lot more waste in our process than is generally recognized. If you're not measuring it, you don't know what it is, and not many people are measuring it. When you do measure it, you're almost certainly going to find out it's a lot more than you thought. So this cost of quality, of course, interesting to measure it in retrospect, but we have a saying in the western part of the United States, no use in closing the barn door after the horse has left. So it's good to look retrospectively, look back on what the outcome of the project was, but we're not going to be able to change it then. We can see what it was, we possibly can learn something from that, but the horse has left the barn. He's out running in the pasture. We're going to have to go see if we can corral him. So better than measuring retrospectively is to measure forecast prospectively, to model what is likely to happen if we do this, we do that, we do the other thing. And in the context of defect containment, there are two important factors that need to go into, that we need to have available to us in order to do this kind of modeling, this kind of forecasting, what the likely consequences of different choices are on delivered quality, cost, schedule. So the first one is what Capers calls defect potential. And that is, he has come up with, again from his database, defects per function point associated with different phases, if you wish, of the life cycle, or different attributes or work products associated with software development. So he says that 0.75 defects per function point are introduced during the requirements phase. So on average, 0.75 defects per function point originate in requirements. Now, we'd all recognize requirements are never perfect. We always make some mistakes there. An additional 1.5 are introduced during design, 1.75 during code. He says have 0.5 associated with documentation errors. The numbers I put in brackets there, I've basically taken the documentation errors and proportionately allocated those back to requirements, design, and code. That simplifies the use of these numbers for modeling purposes. And then, of course, there's another source of defects is bad fixes. So we find a defect, we fix it, but the fix itself is defective. Second thing we need to do this modeling is an understanding of the various defect finding methods that are available to us. How effective are they? What percentage of the defects that are present are they likely to find? And again, these are data from Capers, published in his books, Applied Software Measurement. Anybody who's interested in measuring this stuff really ought to read these books. He's got a wealth of knowledge in several of his books. I think he's published 13 of them altogether now. And this is one of the best ones, in my opinion. It's in the 3rd edition now. And so he's given us some figures on the percentage of defects that are likely to be removed by various testing strategies. So unit testing, function testing, integration testing. He gives a longer list than this. I've just extracted a few of them. And as you see, 25 to 35% of the defects that are present are likely to be found by any given one single stage of testing. So on average, maybe something like 30% of the defects that are there when we do unit tests will be found by the unit tests. So in other words, 70% of the defects that are there won't be found. They're going to roll down to the next stage. So in function test, we find, let's say, another 30%. So now we're down to 30% of 70% is 21%, so there's what, 49% remaining. As you see, some of you might be familiar with the old Greek story about the frog jumping halfway to the wall. It never gets there. And no matter how much testing you do, as you probably all know, you're never going to get all the defects. But to get to 95%, you're going to have to do an astonishing amount of testing. More testing than you're really ever going to be allowed to do. Budgets simply won't allow enough testing to get to very high reliability, very high defect containment rates. That's one of the reasons it's very important to use a defect finding technique such as inspections, because they are much more efficient. They'll find 60 to 90%, or 60 to 80% of the defects that are present. They're labor intensive, but nonetheless still cost effective to do. Okay, so we have two sets of facts here. How many defects are likely to be there at any given stage of the process? And given the various alternative ways we might go about finding defects, what percentage of them are we likely to find at each stage by using various methods? So with these facts, we can put together a model. I put together such a model in my book, and the principal objective of that was to enable what I call leading indicators. So I'd really like to know during the project how likely it is I'm going to be able to deliver to the quality target that's been established. I'd rather find that out early. I'd like to get an update at frequent intervals as I go through the project, rather than wait till the end and see what the result is. We call those leading indicators. If we understand what our containment rate is at the end of requirements, or at the end of design, that's a good predictor of what our end result is going to be. So it's a leading indicator. So this model has two objectives. First, it is to predict delivered quality, and second, to enable us to calculate total non-value added costs. So I just described briefly what I mean by non-value added costs. Let me say a little bit about the terminology non-value added. The cost of quality discipline has been around for 30 years, 40 years, a while. It's evolved and been applied to software. Unfortunately, the term non-value added has kind of a pejorative connotation to it, I think particularly for testers. By definition, in this cost of quality framework, testing is not value added. If the customer had a choice, they would prefer that the product be developed perfectly and that no testing be required. They'd rather not pay for testing. It's not delivering functionality per se. Now, of course, we all know because it's technically not value added does not mean it's not necessary. Clearly, it is necessary. But, on the other hand, from a customer's point of view, they'd like to see us keep the cost of doing that down to the lowest level possible. If we could test it all in 10 minutes, they'd be happy. Now, we know we can't, but still, as a goal, to meet what our customer really wants, we want to try to reduce that cost as much as possible without compromising the delivered quality. Because as we'll see in a few minutes, if we deliver poor quality, the total cost of ownership is going to go way up. It's false economy. We might look efficient strictly from a development delivery point of view, but when you consider the post-delivery costs, it could be very, very inefficient. So total non-value added cost, we want to be able to model both pre-release and post-release. Because we could look real good pre-release and be absolutely awful post-release. It's kind of an old joke in the field. If you don't care how good it is, I can deliver it tomorrow. You know? So if we're going to deliver reasonable quality and control the total cost of ownership, we've got to pay attention to that. So we want to predict defect insertion. Now, I've given you some benchmark numbers from Capers. Now remember that all benchmark numbers, all these published data, represent a distribution. So we're looking at a central point in that distribution. There are examples that are far worse. There are examples that are far better. And of course, most organizations don't know at the outset what their actual insertion rates are. Very few know. The data that's been collected by people like Capers is taken retrospective and backed into what were these numbers, what was the range of numbers that existed. But when you're starting off and you want to try to forecast what your cost of quality is going to be, you don't know what your number is. So probably you're going to use one of these industry benchmark numbers as a starting point and then see how the predicted results compare to the actual results. You might find you insert fewer defects than averages suggest. You might find you insert more defects than averages suggest. Your containment might be better, it might be worse. So we want to predict defect insertion. Generally, we're going to start with the published numbers and then refine those over time to more accurately reflect what the reality is in our situation. So we focus on defects. And defects account, as we saw in the cost of quality numbers, they account for the largest share of development costs in most cases. In an average case, 60% of total development cost is associated with finding and fixing defects. Second thing we want to do is enable us to have a way to monitor early in the project the relationship between the number of defects that are likely to be there and the number we've actually found. So if we're doing a 1,000 function point project, and we use Capers benchmark numbers, we would expect 750 requirements defects to be there. So we're working on our requirements, and we found 500. We found 2/3 of them. How good do we feel about that? Is that okay? I would feel pretty uncomfortable myself. I'd like to see a number well over 80%, and hopefully in the 90% area. So if I'm early in a project like that, and I've got a measure like that, I know it's not precisely correct, but it gives me a sense. It gives me a number that allows me to form some impression. It's not entirely subjective about how are we doing. Have we devoted enough time to finding the defects that are present in the requirements? We know there are defects there, and there may be 750 or there may be 500. But if I've only found 200, I could be pretty sure I haven't done enough yet. Another thing this model does is allow us to estimate the effort that might be needed to execute sufficient appraisal activities. Now, I'm using the term appraisal in the sense of anything we do to find a defect. So testing is one kind of appraisal. Fagan-style inspection is another kind of appraisal. Informal reviews are another. There's many different kinds of appraisals. Appraisal broadly means any activity we do that's principal objective is to find defects. So one of the things we're trying to do with this is give ourselves a sanity check. So let's suppose that we have a project that's spent 3 months gathering requirements, and our work plan includes 1 week of requirements review. Does that feel good? If there are 750 defects there, can we find them in 1 week? Come on, let's get real here. So let's do a sanity check. Let's do some forecasting. Let's think about, is this realistic? Can we actually do this? Without these numbers, we don't know. It's all gut feel, and usually it's wrong. That's why so many projects get in trouble, why they run late, because they're not realistic about the amount of effort that needs to be devoted to finding the defects that are there. Another thing that we can do with a model like this is forecast both pre-release, that is before delivery, and post-release, after delivery, non-value added effort. So when as I alluded to earlier, when the delivered quality is poor, our defect repair costs, our post-review costs can be 50% of the original budget or even more. So we need to manage total cost of quality. I see I'm running late, so I'm going to speed up here. Cut through all the nonsense. You can get this. I'll be happy to give you this model if you'd like to use it. Try it out for yourself. When you execute it with a reasonable set of assumptions and parameters, you get the results that look like this. Basically, I modeled 5 scenarios here that roughly correspond to CMMI level 1 through 5. At level 1, we're probably going to deliver total containment effectiveness around 83%. At a level 5 kind of scenario, we're going to deliver something close to 98% containment. And this is looking at the efficiency of all this. What happens to non-value added costs as we get better? And you can see our total non-value added declines dramatically as we get better at defect containment. So I think this demonstrates the argument that better quality means lower cost. So getting started on this, consider a radical external strategy, differentiate on quality. I know that's very hard. Competition is generally on cost and on schedule. But if we are brave and we try hard, we can probably differentiate on delivered quality, which means we're going to have we, the development team, are going to have lower warranty costs. The customers are going to have lower total cost of ownership, and they're going to give you great references. You can engage your customers in a dialogue with this. You've got to be open with them. What's the real facts of this matter? And that's hard, So internally, very important that we value facts, that we walk the talk, sort of associated with the theme of the conference. So we've got to trust the team, we've got to be realistic. This is very important for managers to hear this message. We might want to think about having a quality incentive program, set specific targets, initiate improvements, use a scientific approach like DMAIC and Six Sigma method or PDCA, an older similar method. If we're going to make that work, there's always a trust issue. People feel like, why are you measuring me? Are you trying to judge me? Are these measures going to be fair? Are they going to be used appropriately? So sharing the strategy and goals of measurement is important. It's important to improve the defect tracking systems. It's very important to understand that we're measuring the process, not the people. That's never going to work. So key challenges, how do we get practices that we know work? The evidence supporting what I've suggested to you is overwhelming, beyond dispute, but not widely used. Why is that? Very strange. Is it because we don't know? Is it because we're afraid to try something new? Is it because management won't allow it? Hard to say what the reasons are. They may be different in different situations. So, second big challenge is how do we communicate to management the fact that 95% TCE is faster and cheaper than the way things traditionally have been done. Final thought, finding defects in requirements is the single most cost-effective way to improve delivered quality. According to Capers, 17% of defects originate in requirements. On average, only 77% of those will be removed before delivery. So a third of the delivered defects originated in requirements, and they're always much more expensive to fix. So testers, thinking about what testing means in broad sense, can play a key role in finding requirements defects. In fact, the session I'm going to do tomorrow, workshop 6, is going to talk about the tester's role in requirements. We'll be talking about some parts of the Certified Professional for Requirements Engineering. So thank you all very much. Appreciate the opportunity to be here.